radian. Number 6 was just a fill-in of a formula, I'm pretty sure. One of those application formulas, you probably had to dig for it just a little bit. Number 12, A was quadrant 4 and B was quadrant 2. Number 16, to get coterminal angles. This was stuff from the video that you guys were supposed to watch. That's still in Google Classroom if you haven't yet. To get coterminal, you have to add or subtract 2 pi. I think they said one positive, one negative. So adding and subtracting 2 pi was totally good for the first one, but check it on the second one. This is negative 2 1/4 pi. By adding 2 pi, you're still at a negative, so just go ahead and add another 2 pi. You can add from here, or you can add from here, and that would make it positive. So adding 2 pi wasn't good enough. It got your negative one, but you should have just added another 2 pi to get that positive one. Strategy changed just a little bit. What were you doing in this one? Graphing? I think you were graphing. Negative 30 is in that fourth quadrant. Negative 750 is you go. Remember, negative is clockwise. 1 full rotation, 360, 2 full rotations, 720, and a little bit more. You actually end at the exact same place. It's a coterminal angle. Complement versus supplement. Do you guys have a way of remembering complements go to 90 and supplements go to 180?
Because like when you're older, you need like a lot of supplements for like.
Oh, there you go. So it's the bigger one?
Yeah.
That's a good way of remembering it. I would have never thought of it that way.
New drugs.
Great. Not really. 180 minus 46. So supplement adds up to 180. I'll take that. The older you get, the more you need to supplement your nutrition, etc. Sure, why not? And then going to 90. However, in letter B, what's with the whole not possible thing? Yeah. If you were to try to get to 90, you'd have to do a negative angle. It's bigger than 90, so it doesn't have complements and supplements. I know it's in the video, but you guys weren't able to like visualize me doing it. A complement is what you need to add, specifically add to get to 90. So what's missing to get to 90? But 93, it's already at 90 and over. You can't add anything to get to 90. So it's already too big. So if you ever go bigger than 90, there is no complement. If you were to ever go bigger than 180, there is no supplement. Just as far as like vocab goes. Oh, that's why. Because it was the video. I was like, we never talked about converting from degrees to radians or radians to degrees, but we did just on the video. Anyway, converting to degrees, got him. Converting to degrees, got him. You're multiplying by degrees over the understood radians. Radians aren't actually written, but they are a unit. The pi's do get to reduce. They do go away, but numbers are left over. 52 was, I think these were like application problems, right? It's not the main point of the chapter in any way, shape, or form. It's just showing you some things to do with arc length, because radians are arc length. Radians occur naturally. So if you were to plug in an angle, you cannot just plug in 150. This formula, this physics formula, needs radians. Radians are the naturally occurring. Radians have to do with arc length, not degrees. Degrees are that man-made construct. So we have to convert the angle before plugging in, which is why in the video I should have made a big deal about how we have to only use angles and radians for those word problems. And 76, I do not remember even what that was.
Oh, I think I wrote it.
What was 76?
Is a degree or a radian greater than?
Oh, it was an easy question, and they have this huge paragraph to explain it. We talked about it. A degree is how much of a tick mark on a protractor?
That's a different
One.
one.
A rate, oh, it's a different question. Okay, then forget this one. This is the wrong question. Laurel, I see you. Give me 1 sec. 76, who's bigger? The little tick mark on a protractor or one full radius going around the circle?
I put radian.
Yeah, 1 radian's much bigger. And if you were to actually like convert a radian, in case you're curious, because you could have actually gotten radians in terms of degrees. Love my computer, not really. How would you convert 1 radian? This is actually a really practical skill.
I have to read that one by
What would you guys multiply to convert 1 radian to be degrees?
180 degrees.
Do you need a degree degrees on top, right? And then what would be down? Pi radians, right? Don't we need to have a match? Now we don't usually write radians. Talking, please learn to whisper. Don't talk louder because I'm talking. That kind of defeats the purpose of me talking. Understood radians cancel out, but the pi doesn't. The pi is still there because this one radian doesn't have pi. So if you were curious as to how many degrees are in one radian, 180 divided by pi is going to be, I think, 59, 58, 50 something, something, something. We could do it quick. Laura, what's up? 57.296. So what's bigger, 1 degree or 57 degrees? Oh, come on, it's obvious. 57 is bigger, right?
No.
Is 1 bigger or 57?
57.
Who was 57?
1
The radian. Good. So is 1 degree or 1 radian bigger? 1 radian is definitely bigger. It takes 57 degrees to make 1 radian. Okay, any other questions you guys have on section 4.1? Sweet, section 4.2. This one was like actually finding sine, cosine, tangent, cosecant, secotangent using HPrecalc or SOHCAHTOA. Wait a minute, I don't have a triangle. I don't have opposites and adjacents. I have x's and y's. But if you like triangles, couldn't you have made one?
Looks like a shark thing.
Hmm?
Oh, look at the shark.
Oh my goodness, Sophia, now you're trying to distract Alec.
What a reverse card.
Yeah. What quadrant should this be in? And why do I need to erase my triangle?
Because it's not in the first quadrant.
It's not in the first quadrant because x is negative. So in what quadrant is x negative and y positive? A negative x says move to the
2, it's in quadrant 2.
left, and then a positive y says move up. This would be the proper placement of my triangle, right? The x would be negative 8 over 17. How far over? The y would be 15/17. Technically it should be taller, but whatever. And then in the unit circle, what's every z, or what's, yeah.
Nissan.
So if you like SOHCAHTOA HPrecalc, you can technically fill in a triangle with exactly the information they gave you. And then I know the angle is technically, maybe you don't know that the angle is technically way out there, but we still use what we call his reference angle. We would name him something different, but we use this triangle to answer this angle's trick. So sine, opposite over hypotenuse, got him. Cosine, adjacent over hypotenuse, got him. Could you memorize? Who goes with who? Yes, you could. And put in the x for the cosine and put in the y for the sine. Yes, you could. But could you also make a little baby triangle and just use SOHCAHTOA HPrecalc? Yes, you could.
If you wanted to be that snazzy.
What, Sophia?
If you wanted to do that.
If you wanted to. Some people, the visualization helps. It just depends.
It sounds pretty snazzy.
Okay, number 18. How did they find it?
Oh no.
Can you guys tell that, well, can you tell that they're using the circle, right? Because they're taking this, they must be locating a spot, and the spot has an x and y, and then they're putting the y in the sine spot, the x in the cosine spot, and the y over x in the tangent spot. But what's another way that you could have done this? Yeah, with the cheater chart. Because you would have been looking at your pi over 3 column, I hope, and your pi over 3 column would have been 1, 2, 3, 3, 2, 1, all over 2, square root 3 over 3, 1 square root of 3. Okay, that would have been my pi over 3 column, and that would have been for my, remember, SOHCAHTOA, so my sine, my cosine, and my tangent. Can I just steal? Hey, sine, cosine, tangent. Almost. What else do I have to think about? How can you determine the negatives without the circle? Yeah, you could have figured out what quadrant he's in and then say, hey, they're all positive. The sine ones are positive, the tangent ones are positive, the cosine ones are positive. So where would negative 4 pi over 3 land? What quadrant?
Tangent.
What quadrant?
2.
2.
Why 2?
Because it goes in bars.
Negative.
I'm sorry.
Negative's not going up, negative's going down. And isn't this 1 calzone and an extra third, right?
No.
So it's all 3 over 3 and an extra 4 over 3. Remember fractions? 1/3, 2/3, 3/3. I can always think of pi as 3/3. Or if he was 6, I could think of pi as 6/6. If he was fourths, I could think of him as 4/4. This location will always be all the pieces, right? So I have all 3 and 1 more. Second quadrant, who's positive? Sine and cosecant, if I was to do that, 1 over sine. But everybody else needs to have a negative. So I take my pi over 3 and say, you two need to be negative. Dun, 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 dun. Without ever having to actually use that weird like XY stuff if you guys don't like it. But if you do use the XY, you could have landed here and said, oh hey, it's over an Emily and up a me.
Oh, yeah.
Right? It's over the little one, 1/2, but it's left, which would be the x, or the cosine. And then it's up, the tall one. Up is a positive, and that's the sine. So if you guys ever hear me say like, oh, it's over a little, up a lot, over a lot, up a little, I'm visualizing where this is landing in the unit circle, because that's how I usually think of it, with the x's and the y's matching up with sines and cosines. But I like to think adjacent and opposite. It helps me make a match with SOHCAHTOA. Why am I taking time in grading homework to talk about the unit circle again?
Because it's very important.
It's important, and I'm trying to show you there are different ways of thinking about it. You don't have to have the Mr. J fill-in circle way. You can have the cheater chart way, or you can have the triangle hits here and just think over and up and how 1/2 is the smallest and root 2 over 2 is the middle and root 3 over 2 is the biggest. There are different ways of thinking about it. And if you're not sure which way you're going to choose, come see me. We'll grab a whiteboard and we'll try to figure out which one makes more sense in your head. I've done it for several kids. I could do it for you too. Okay. This one is negative pi, which is super awkward because he would be on the axis, and these ones are kind of weird. Not that you can't still use the idea of a triangle, it's just kind of awkward because your triangle is flat. So your opposite is 0, your adjacent is -1. Maybe the point might be the easiest thing to think about. It might be the easiest thing because there is no like actual triangle since it's on the axis itself. It's a poor little flattened triangle. But if it's flat, well then my opposite is 0, so my sine is 0. My cosine is that whole length of -1. Tangent is this guy over this guy, and then I can go ahead and flip. Where does pi show up in my cheater chart? Because some of you are like, I think I like that cheater chart idea. Where does pi show up in the cheater chart? He's not a 30, he's not a 45, he's not a 60, he's not a 90. He's not this, and he's not this, and he's not this, and he's not this. Who must he be?
One.
Wait, how does that work?
Oh, okay.
Oh, because 0's on this side, pi is just the flip of that, right? So if you were looking for him in the cheater chart, you would look at this one. And remember, 1, 2, 3, oh, it counts up. 3, 2, 1, oh, it counts down. And then sine over cosine is tangent. So if you were thinking about your SOHCAHTOA, if you were thinking about your SOHCAHTOA, you could plug in from, except he's pi, well he's technically negative pi, so he's getting there a different route, but he's still landing at the same place as positive pi. But yeah, that x will be negative, just because of that left direction. And then you can fill in, you can switch in 1 over 0, that's under fun. 1 over -1, -1, 1 over 0. Number 40 was fun. Or was he?
Oh yeah, he was fine.
You just needed to look at those properties I had you write down yesterday, right?
Yeah.
That was the one example that we didn't get done, was what do we do or how do we use those even and odd properties I had you guys write down somewhere. So here somewhere. Here. How do you use them? Well, in your homework you have to match it up and say, okay, cosine goes with what? So if I'm doing like cosine of negatives or secant of negatives, where do they match up? And cosine matches up in the, oh, it stays, the sine stays the same, and the sine stays the same, so check it. The sine stayed the same. Wait, why is he flipped? Oh, who's secant again? Cosine's A is a yes. Since the guys are non-zero, then everybody's going to work. The only problem is when we have zeros. B, everybody's negative in the third quadrant except for tangent and cotangent. All students take. Everybody's negative except for tangent and cotangent. So A was yes. As long as there are no zeros, everybody's going to exist. And then B, in the third quadrant, everybody's negative except for tangent and cotangent. And then we finally graded section 4.2. It's all in the YouTube video for those of you guys that are still trying to catch up. But do you guys have anything in 4.2 that we need to go over? I'm hearing talking, but I'm not hearing problem numbers. Anything? Okay, so the answer is no.
No.
Got it. Here we go, section 4.3. Beep.
Blue and reverse card.
Wait a minute. Hold on. Pause. You guys were writing this down at the beginning of class, right?
No.
Oh, well, awkward. Here we go. But check it. Is this super new?
Yes.
Yeah, and I've actually talked about it, right? Because I've been talking about the unit circle in terms of triangles. Guess how our book teaches the unit circle? Like Mr. Che did. It's all about the circle and it's all about the points. I brought in geometry because my head likes the triangles better. But the nice thing is we've already kind of done section 4.3 in some ways. Section 4.3 says we got to think about triangles. Yes, you can think about them in the unit circle. Yes, you can think about them in the unit circle, but okay, we know that triangles can show up outside the unit circle. So to be ready for triangles, however they appear, well, let's just do the good old-fashioned. O for opposite. A for adjacent. H for hypotenuse, right? Yesterday you guys should have finished up the unit circles, and I realized I never passed around any sort of tape or stapler or anything else to put it in your notes. So if you want to attach it, I think that's a good idea. You can use the tape, and if you don't need it, you can just keep it passing. But to be honest, you just need it somewhere in section 4.2, section 4.3, the unit circle. 4.2 is the best place, but some of you might not have space. You can throw it in 4.3. But guys, I could also theoretically say like an x, and I could theoretically say a y. I mean, I could be all snazzy and actually use variables. Or like an a and a b and a c, like a squared plus b squared is c squared. Like I can use other things, but what are you mostly used to? Right? Yeah. So, okay. Yes, I get that O can look like 0, but if we just realize it's a right triangle, hopefully you know, oh no, opposite. But technically, if we were to need to make sure everything was okay as far as variables, you could think opposite over hypotenuse is like y over z. Adjacent over hypotenuse is like x over z. Opposite over adjacent is like y over x. You can think about it with letters, but just realize it's the same thing as your sine equals opposite over hypotenuse. Cosine adjacent over hypotenuse, tangent opposite over adjacent. Cosecant could flip it and say z over y. Secant could flip it and say z over x. Cotangent could flip it, x over y. And if you're outside the unit circle, well, that z could be a number. The unit circle, the hypotenuse was 1, the radius was 1, but, well, anyone else. You have a ladder leaning against a building. Okay, the ladder's going to be something more than 1, probably. Like a 6-foot ladder or a 10-foot ladder. One of those cool, like, retractable ladders.
I have.
I should say extension ladders.
Or a Minecraft ladder.
Sure.
The most functional of all ladders.
I need a ladder to get up to my Christmas decoration.
I can't climb ladders.
I have a condo with like really high ceilings, and there's like a big old ledge that I can't even touch the top of. And on top of that ledge is that. That's the one. That's big old sitting.
That does not sound like that was a...
Anyway, so we go with Tropical. Because CHO is cosecant, hypotenuse over opposite, S is secant, and C is cotangent. Flipping all of their reciprocal functions. Okay, we got them, right? We should?
Yeah.
Dual page just in case someone's lagging behind just a little bit. Patience is a virtue. So, what kind of problem is this? The clue.
The boomer type.
The clue is that sine of theta equals 0.6. The directions, the mission is to find cosine and tangent of this angle. Now just a few of you might be like, oh hey, inverse trig is a thing. In my calculator there's a second sign. I think I get to go backwards. That's not what this problem is about. Not saying you couldn't do it that way, it's just not what it's about. All I've done so far is said that in this section, trig comes from triangles. So here's my question. What's my triangle?
My bad paper.
What's my triangle? All I've said so far, trig comes from triangles. So what's my triangle? Good. What do I know about my right triangle? Who's this guy?
Oh, and then that's 90, right?
Mm-hmm. That's 90. Here's my theta. Oh, because sine is opposite
That'll do.
over hypotenuse. Mm-hmm. Very funny. Let's not injure him anymore. Where is 0.6? Where could that have come from?
6 over 10.
Yeah. Where else could that have come
2
from?
over 3.
Huh?
2 over 3.
Just for like 5 seconds.
Not 2 over 3.
2 over 5.
Not 2 over 5.
3 over 5.
There you go. Okay, are there a lot of different places this could have come from? Mm-hmm. Could it have come from like 60 over 100?
Mm-hmm.
Right? Like there are lots of different places this could have come from. So let's just use one example. Because the nice thing is that whatever triangle it came from would be a similar triangle to this one. Which one? Well, I don't know, it's up to you. You could do 6 over 10, but if we're doing triangles, does anybody like it when we have 3's and 5's in there?
I do.
Because the last one is then a 4. Now, could you have done Pythagorean theorem with 6 and 10 and figured out the last one is 8? Yes, 100 minus 9 is... Wrong way. 100 minus 36 is 64.
No, these are.
But either way, whatever triangle this did come from would be proportional to this one from the whole idea of similar shapes in geometry. If it was a bigger triangle than this, well, to have this sign, it would have still had to have had sides in the same proportion. So you can multiply everybody by 2, you can multiply everybody by 3, you can multiply everybody by 2.5. It would have to be a proportional triangle. So the nice thing is, I don't know exactly if this was the triangle that got the 0.6, but I know that whatever the triangle is it did come from is proportional, which means its fractions, its ratios will be the exact same. So then, what would cosine be?
I'm confused, Ms. Steve.
Well, I changed 0.6 to be fractions, and I could have used, Alec, any fraction that reduces to be this. I could have used any fraction to set up my sides.
So you just simplify the whole 0.6 is all that you did?
Yeah,
Okay.
yeah. And then I said, hey, you could be an opposite, and you could be a hypotenuse. And then I solved the Pythagorean theorem, the guy I didn't know. But a lot of us have this one memorized, 3, 4, 5. So then I just ask myself, if I have a triangle, what's my cosine? Everybody should answer. Mm-hmm. But probably they want decimals because that's how they gave me the information. So 0.8. And then what would tangent be?
3 over 4.
Opposite over adjacent. If you can make a triangle, I don't need to use that weird little button in my calculator that says I'll go backwards from a trig to get an angle. I don't need that. I can just use my triangle. So Victor, what Joshika? But I want a fraction. If I have a fraction, I can then go ahead and fill in sides. And if I have 2 sides of the right triangle, I can always find the other one. And I can tell you whatever trig you want to know.
Misty,
Yeah.
if you didn't know that it was supposed to be like 3, 4, 5, would you have done like 3 squared plus 5 squared?
Yeah. You could have done your c squared minus b squared. It's just a rearrangement. Equals a squared. And that's how you get your square root of 16 is a.
Oh.
Which is
4? I thought that was 9.
No, that's not 4.
No, the A.
Or an h is an h.
The A.
Oh, the a, yeah, it's a squared. A squared plus b squared is c squared, yeah.
Imagine having 2.
Wait a minute, so what on earth is on this page? Let me zoom in a bit. Oh, these are relationships, it's a thing. Like how cosecant is 1 over sine. We're used to this one. And to be honest, let me highlight it because these are probably the most important reciprocal identities. But if these are true, cosecant is the reciprocal of sine, technically this is true too. Sine is the reciprocal of cosecant. Now careful, kiddos. As you're writing this table down, I need you to realize, even though they don't show it, it is important that we think of the trig with having parentheses. Very similar to log having parentheses. Very similar to a square root in the olden days having a parenthesis. In the olden days, you didn't have the really cool operating systems in your calculator that would make it all nice and pretty and make it small underneath. You'd have to say square root of what? Of x. Logarithm of what? Of theta. Sine of what? Of theta. It's an of, it's not a times. It's an of, not a times, because these are all f of thetas, right?
Trig prop.
You can't take away a sin from the theta, because the theta is stuck in the sine.
Theta. Sin is our fate.
No,
Oh,
it's fate.
probably.
Fate.
Yeah.
But it could be sine of t, and it could be sine of a, and it could be sine of, they could make it whatever variable they want. Just theta is a pretty common one. And then we have these quotient properties. If tangent was y over x, the nice thing is it's also sine over cosine, which is helpful in our cheater chart. So I can do sine over cosine equals tangent. I can make little baby divisions as I fill in my cheater chart. Cotangent's just the flip. And then I have these cool Pythagorean identities, which might seem kind of random until I throw up that triangle, or a version of a triangle from the unit circle. Ooh, pretend that's a nice circle. That's a rough one. Remember how we talked about how sine is cosine and y is sine, right? If that's true, couldn't I label that? You had to use it all last homework. For a certain theta, the x in the unit circle is cosine, the y in the unit circle is sine. Isn't there a relationship with any right triangle that says side squared plus side squared is hypotenuse squared, right? A squared plus b squared is c squared, x squared plus y squared is 1, cosine squared of theta plus sine squared of theta is 1. Oh, just Pythagorean theorem. Oh, that's why it's called a Pythagorean identity. And I could technically do triangles for the other two also. They'd be kind of messier, because we have to use these reciprocal identities from up above to be like, wait, so sine could be rewritten as 1 over secant.
Ew.
Or 1 over cosecant, sorry. So I'm not going to like keep this in this main page of notes. Let me just show it over here real fast. I could rewrite that triangle in the unit circle as, let's see, sine would be 1 over cosecant of theta, and cosine would be 1 over secant of theta is 1. I could have tried to do that. So that would have been 1 over secant squared theta plus 1 over cosecant squared theta. And you might be like, wait a minute, whoa, 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 what are you doing? I thought that the whole cosecant of theta was squared. Why are you putting the squared on here on the inside? It's notation. Whenever you square a trig, 1 squared is just 1. Cosecant theta squared, while this is right and it totally maintains the meaning of the whole guy being squared, if that's just an of theta, I can kind of use some of that function notation to be like, oh, I can make it look a little prettier. Means the same thing. Means the same thing. Notation might mess you up from time to time, so it's good to know that you can bring that little squared in. Ew, does that look like any of those other two formulas? Not really, huh? But what we could do is, well, do either of these formulas have fractions? Not really. Well, what if I was to multiply both sides by, to get rid of fractions, I'd have to multiply by the denominator. So I have to multiply secant squared times cosecant squared. Secant squared times cosecant squared. Which, if I distribute that to both, this guy would lose the secant squared but keep the cosecant squared. Oops. Plus. This guy would lose the cosecant squared and get to secant squared. Ugh. Oh, hey, one of the formulas has a secant squared over on that side, right? Oh, and the other one has a cosecant squared. Hold on, I think I can use this to get both of them. Okay, if I was to try to keep the secant squared, who would I need to lose? For the first formula, I need the secant squared to stay. So who do I need to get rid of?
Cosecant.
Okay, and the way to get rid of him, well, it's multiplication, so what would I do? Divide. And so if I divide, I would get, everybody has to divide to be legal. This guy would need to divide also. That's the same thing, right? Wait, huh? I thought it was supposed to be 1 plus tangent squared. Oh, 1! Hey, look! What's cosecant squared over cosecant squared? 1 plus.
That's tangent.
That's tangent? Are you sure?
Yes.
Wait, secant squared. Didn't secant come from 1 over cosine a long time ago? Oh, so this could be 1 over cosine squared all over 1 over sine squared? That's tangent? That's tangent.
Tangents.
How is that tangent?
Because of Mr. Hart.
No, that made no sense. If I divide by 1 over sine squared, doesn't that mean I'm multiplying by the reciprocal? And if I'm multiplying by the reciprocal, who is sine squared over cosine squared? Yeah. This one up here tells me tangent is sine over cosine, so if they're all squared, hey, it's tangent squared. Now, some of you are like, it's written right there, can't I just memorize it? Yeah, you can. I'm just showing you that technically it comes back to a Pythagorean theorem also, just if you were to write this as 1 over cosecant and him as 1 over secant. You can actually get there from the Pythagorean theorem, but you have to play with all these formulas. And this guy would be super, super similar. I would just divide, instead of by secant squared, I would divide by, instead of dividing by cosecant squared, I would divide by the other guy, secant squared. And this time my 1 would end up in, oops, the secondary spot. And if you were to change cosecant squared to be 1 over sine squared, and change secant squared to be 1 over cosine squared, you would end up with the flipped property, the flipped quotient property, which matches with cotangent squared. But some of you might have realized that was a mess to get to, right? Did it come from a Pythagorean theorem of a triangle? Yes. But was it nice?
But no.
Do you want to see a simpler way to get there? And the only reason I'm saying this, guys, is a lot of people remember the very, very first one. Sine squared plus cosine squared is 1. A lot of people remember that one. But they tend to lose these two, and the sad thing is those two are also important. So I'm just trying to get you a way to remember. If you remember the first one, how do you get to the second two? Okay. We can cheat the process a little bit and not have to go through all that craziness if we just remember one thing. The first guy has sines and cosines. The second guy has a tangent. Wait, whose tangent again? The quotient property is opposite over adjacent, but the quotient property says tangent is sine over cosine. Hey, I have a sine. I have a sine squared. I need to put him over a, ready? Divide everybody by a cosine squared, and there's your tangent squared. I just need to ask yourself what's left. You remember tangent is sine over cosine. You can make your tangents, oh, there he is. Tangent squared plus 1 is secant squared. Aha! I got one! Just by remembering a tangent is sine over cosine. So if I remember the second Pythagorean has a tangent, I'll just make him. And I can do that in math as long as I do it to everybody. And the third property has a cotangent. Who's cotangent? Okay, that's one way, but I don't have any tans. What is cotangent in terms of sines and cosine? Cosine. I got one. I'm going to make a cotangent. Oh, but what did I do to one place? I have to do to everybody. That's a lot faster than all that other crazy stuff, right? It's kind of just a spiffy way of being able to take the one that everybody remembers the quickest and use it to get the other two that most people tend to forget. Okay, but some of you realize I kind of left out something. Sine squared equals. If we were to look at this table, maybe you guys just figured out the point isn't necessarily to just memorize the table, but be able to use the table. Now, in case you were just like, oh, she only highlighted those ones. I only, oh, no, sorry. They're all important. These ones are a little bit extraneous. I don't want to say extraneous. That means like not valid, but not used very often. But everything else, you're fine. Some of you are going to be like, you didn't say we had to remember. Okay. Is there in this chart sine squared equals? No. Oh, so it doesn't equal anything. Wait, play around with some formulas.
Sine equals that.
What could sine squared equal? 1 minus cosine squared. Couldn't I rearrange a property to get a sine squared alone? What else could you do? Ooh, could you say sine squared is equal to 1 over cosecant squared, which is 1 over our snazzy notation? What else could sine squared equal? Ooh. Couldn't he also be? Careful, not cosine over, but wouldn't I have to multiply? Couldn't I have it be cosine squared times tan squared? Oh, stink. There are a lot more formulas that could come. Yeah. Danger. With this table, even though it's good to memorize the whole thing and it's very fundamental to have it all down, okay, these are kind of a little bit weird, but the rest of it down, you need to be able not just to know it, but be able to use it. So if you see a sine squared, you're like, oh, I have a formula that I can rearrange. Rearrangements are totally valid. Priyanka, what's up? Okay. Oh, we already did that. We already did that. So, what am I supposed to do? Prove it? No, careful. Don't worry. Not geometry, not 2 column proofs. You don't have all these corollaries and theorems and postulates. You have a table of properties. Is there something that you could do in the table of properties that would show definitively, without a doubt, that this is true? What could you do? You could divide by and say it matches, but it's better to not move one side to the other, but to actually just either make this guy look like 1 or make that guy look like him. Think about it this way. He's your given and he's your proof. I know, okay, kind of like geometry. You have to make the given match the proof. You can't go like mixing the two together. So is there something that I could substitute for tangent or cotangent to make it mathematically make sense that it's 1? Oh, yeah, tangent is sine over cosine, quotient property. And what's cotangent? If you use the quotient properties, mathematically, doesn't it make sense that 1 equals 1? Ta-da. Couldn't you also have used the reciprocal property, though? Couldn't you have also said that cotangent is 1 over tangent? Supposed to equal 1. Oh, yeah. Hey, look. 1 equals 1. You're trying to make the left side equal the right side and or the right side equal the left side. So, any ideas on the next one? What do you guys think? Do math or plug in? That's kind of always our options. Do math or plug in? What do you want to do first? Plug in? Okay, so tell me something that secant equals. Careful, they don't have squares. We can't use the Pythagorean properties. 1 over cosine. Okay. If you're changing him, I bet you should change tangent too. He's sine over cosine? We're going to change all of them just to make them look similar? It's supposed to equal 1. I'm not sure I see it yet. Wait, fractions. What do we do if we have common denominators? So now what? Fractions, how do I multiply them?
Cross.
So, cosine times cosine is? That's a difference of square. Oh, that's right. A plus b times a minus b is a squared minus b squared. Oh, this is taking forever. Unless you look at your Pythagoreans and you realize that cosine squared is 1 minus sine squared when you rearrange. Guess what? Cosine squared over cosine squared? 1 equals 1. Bye, guys. Homework not due until Friday, but I would start.